Okay, good morning, good afternoon, good evening, wherever you may be. Welcome to the last of the CSAT 2025 Action Series webinars. I am Brad Richards. I am a member of both Solidus Global and Powders on Demand, and today we're here to see a talk from Steven Camilleri, who is the CTO of SPEE3D. Now, if you haven't been to one of these before, Steven will be live and presenting. If you have questions, please enter those questions through the Q&A function of Zoom. At the end of Steven's presentation, I will relay select questions there, assuming that we have a bunch of these over to Steven, and he can answer them, and we'll have a little bit of back and forth based on that. So without any further ado, Steven, handing it over to you.
Thanks, Brad. All right. Yes, good time of day to you all. So I'm coming to you live from Darwin, Australia, up in the north near Bali. So it's currently 10:30 p.m. So I'm doing that unusual thing Australians have to do where we speak professionally to ourselves quietly in our household in the middle of the night. So thanks for coming along. This is a follow-up to my CSAT presentation. So those of you that were there, welcome back, and those of you here for the first time, nice to see you here. So I'm really trying to expand on the work that I presented at CSAT and get through a little bit more of the detail and the nuance that the CSAT format really didn't give me much time to go into. So let's get into it. We'll start with a bit of history. So there's an image, I think, from 1999. So I'm in the red shirt. Byron Kennedy, my business partner at earlier company IMT and now at SPEE3D, is in the white shirt. And some of you might recognize above our electric bike there, Lyle, one of our programmers, back when he had lots of hair. So we started out as electric vehicle people. So my original graduate degree is in power electronics, and we worked in high efficiency motors. So the technology we developed for our solar car, which was world record holding, went on to dominate the world of high efficiency swimming pool pumps, which is a really sad brag, but each one saved a ton of carbon a year. So we're very pleased with kind of the penetration of that product. So the short answer is going from there, being an EV person, working in high efficiency electric motors, and then moving on to cold spray 3D printing is a little bit of a leap, but indeed it came about as a process of us getting really deeply into mass production and becoming manufacturing engineers after our first tech company got bought out. So we'll move on. So why us? So our technology, cold spray AM, allows us to make parts very, very quickly, even in the field. So you can see here there's an Australian soldier fitting a new bearing seal to an M113 armoured vehicle. This is a common problem with this vehicle, is these things get knocked off. The M113 is a common driver training vehicle, and a handy tree will knock these off, and the bearings are soon destroyed. So they're able to manufacture these new metal covers in the field, in the dust, in a few hours with our tech. So let me give you a bit of a background into how the tech works. So many of you, of course, will know cold spray. So that image to the left will be quite familiar to you. It's really not that different. We've had to optimize our nozzle a little differently to make it very, very repeatable over long periods of time. That's very important for additive manufacturing as opposed to coating or repair. So our nozzle tends to be kind of the long haul freight truck to a lot of other people's, Ferrari and Lamborghini nozzles, which do amazing stuff, but for a slightly different market. So on the right, we have a robot which holds a substrate plate, and indeed we shoot the metal into that substrate plate. The metal builds up, the robot moves around to build up the part. That's how our process works. And it's direct CAD to part. So you bring your shape, and the process gets simulated, and then it will automatically print that part. So in brief, there are 3 process steps in our standard process. So on the left, we have the design stage. So you can see that green cylinder is a simulated cold sprayed part on the end of the robot. So our slicing software, for those of you that know 3D printing, will know about slicing software, which converts the CAD to the toolpath. Also does simulation. So you can see the simulation of the cold spray process. it's a relatively accurate simulation. So all the things that might go wrong in the process as a result of the design being a little bit unsuitable to the printing process, you'll see what will happen in the shape before you print something. So we like to say our labs aren't full of broken parts, because we don't, most 3D printers tend to have a trial and error type approach. We like to make sure it works the first time we try and print it. So the middle column there is the printing. So that's a process part being printed. So you can see that spike in the middle is the cold spray nozzle. You can see the sparks of impact as the powder's hitting the substrate, and indeed the robot arms are hunched over the top, moving the plate around. So on the right there is the last stage of the process where we say we cook and cut. So we heat treat the part, and then we machine the part. So our process is a little bit analogous to powder metallurgy. So, most cold spray is done in a repair or coating context. We don't really do that. We do this design, print, cook, and cut, where we're building a powder metallurgy compact with cold spray and then turning that into a completed part with heat treatment and machining. So the equipment we have now, we have a small size printer that's on the left, that's Lightspeed. That'll do parts up to sort of 5 kilograms, 11 pounds. Our most common product is that one in the middle, Warp Speed, which does parts up to sort of 40 kilograms, sort of 90 pounds. And that's really designed for kind of workshop use, factory use. And then we have another system on the right, which is quite different. This is for expeditionary work. So I've been on probably about 15 trials. Those of you that have met me in person will know I'm a large gentleman, but I have indeed been on many extended camping trips with different armed forces, sleeping in pits and eating rat packs and making parts with that facility and improving our product tech by working with defense forces of many different nations. So we call that EMU, Expeditionary Manufacturing Unit, also because an emu is a famous Australian large bird. So I think those of you in the US will know, I think it's Limu the emu from TV ads. It's actually pronounced emu. So in Australia, we say emu. So Expeditionary Manufacturing Unit. That has all the heat treatment, all the machining, all the testing capability, lets you do the full manufacturing process in the dust. So that's a very popular product of ours. So we also have our twin speed software. You can see on the left there, we call it twin speed because it's a digital twin software. So you can see left and right there, we've got the simulation and the real part. There's very strong correlation between those. We also provide powders as well through Powders on Demand. Brad kindly introduced us. He's from Powders on Demand. And of course, we have a range of services that we provide. So for example, we will go out in the field, we will train defense forces. We will teach them how to do the risk assessments and the safe manufacturing processes and indeed the testing of those parts as well. So here's a great example I'd like to show you. So this is from 2023. So we did a field trial in San Diego, California, and so you can see the two the two silver funnel shapes on the ground there. They're called feet. So these are on the end of two hydraulic rams on a US Marine vehicle called a wrecker. So it's a extremely large 10-wheeled vehicle with a giant crane on top, and its job is to pull armored vehicles out from where they might be stranded, stick them on the back, and then rescue them. Drag them away. So these are the stays that hold the vehicle to the ground so the crane can be used. Now, the vehicle is designed in such a way so that if you have to leave in a hurry, you can just retract the jacks and the feet stay on the ground and the vehicle drives away. So what that means is you tend to lose the feet. So in training exercises, it's pretty common for the troops to get an order, go here fast, set it up fast, go there fast, set it up fast, very demanding training schedules. And at some point, someone will forget to collect the feet after the outriggers are retracted. And what do you do? So it turns out it's quite difficult to get new parts. They're cast. The casting industry is suffering from a dramatic workforce shortage. There are long lead times for both the casting and the quality control processes for casting. So we made one of these. It's about, I guess, about 22 inches in diameter, that part. So it might look small on the screen, but it's actually quite large. It's about as heavy as I can carry. And we made that in a car park at a marine base on a Saturday night. And it went out on a helicopter the next day and got tested in the field. So we were very impressed. It was able to hold the full weight of the vehicle. So just goes to show that it's quite possible to get good material properties in the field, if you've worked hard on making sure the tech works in that situation. All right. Those of you over 30 will probably know Under Pressure, the famous song by Freddie Mercury, Queen, and David Bowie. So this is an AI generated image. I didn't actually get them to pose in front of our printer. So our normal cold spray system operates at 30 bar, about 400 PSI. And we've decided to push things this year. So there are people demanding better properties as sprayed from our process for different applications. So we've decided to try implementing a high pressure system. So typically we run off a compressor at about 30 bar with compressed air. And we decided to more than double that to 70 bar. So really, we've done that to improve the critical velocity of the powder, so the deposition velocity, and improve the as sprayed properties of the material. So at that stage, that's just experimental, but we do have it working. So we're busy working out how we will roll that out to people at the moment. It's been very effective. So of course, we see increased gas consumption goes up, roughly in proportion with the pressure. So if you're consuming nitrogen, for example, you're going to double your nitrogen cost with something like that. But if you need the material properties, that's the trade-off. Of course, we see the increased particle velocity. So increasing the temperature at the stagnation part of the nozzle increases velocity, and increasing the pressure does also. So our machine normally holds the pressure at 30 bar and gives you adjustable temperature. So now you can adjust both with this prototype system. So indeed, we tested this out with copper, and we saw significant improvements in ductility with the higher pressure, so as sprayed. So I reported on this a little at CSAT. I'm going to report on this a little more today. So here's the real test of high pressure, is particle velocity. So ASEA were very kind to loan us a high watch. So we had our first play with particle velocimetry as part of this project. And yeah, indeed, particle velocimetry is awesome. We're never going to be able to go back after having access to this very high quality data. So indeed, our nozzle gives us very high quality velocity groupings. So you can see down the bottom of that chart there, there's a position across the nozzle. So we've sectioned the beam with the particle velocimetry, and all those white dots are the particle velocities, and the red line's kind of a group average through there. So our nozzle's exit diameter, for reference, it's about 6.5 millimeters, which is pretty much precisely where those particles are clustered. So indeed, the nozzle's doing a good job, and the ASEA high watch is doing a good job. So fantastic results, I think, from there. And I'll present some more detail on those now. So I've really included this as a bit of a reference for those of you that are interested in maybe not just how our nozzle works, but how cold spray nozzles in general work. So on the bottom axis here is the stagnation temperature, which is usually controllable on a cold spray system as it is on ours. And I've put a separate line for each system pressure. So each line is a line of constant pressure. And what you see here is the high watch measured actual particle velocity. So this isn't inferred or calculated. This is the actual data measured in the middle of the particle grouping. So indeed, you can see as we increase temperature, we see the particle velocity increase. I've put a linear line of best fit through the points just to make it clearer where they are. And indeed, you see as we increase the pressure, the lines move up as well. So it's often more interesting to capture the gas pressure, but it's very difficult, the gas velocity, but it's very difficult to do that without a particle that's visible and very low density. So we've used cinnamon in the past for that. which is unfortunately flammable, but it has the bonus of making your printer smell like a donut shop. So, you know, it's not all bad. So indeed, as we increase the pressure and the temperature, I've compared those results to the standard Vic Champagne, I think 2015 paper on the axisymmetric 1D estimations for particle velocity. And in fact, what we see is with temperature, it correlates reasonably well, but with pressure, as we increase the pressure, we're seeing a better velocity than the approximation estimates. So at some point, I've got to nail Ozan Ozdemir or someone down to try and work out why that's happening. So those of you that have kind of had a good look at the velocities on the left here will say, well, actually, there's not a significant increase in velocity, like the number of meters per second only increased by 15% maybe over the whole spectrum here. Like, is that really that much? And the short answer is, well, yes, it is. So the factor that actually seems to impact on cold spray more than velocity is the kinetic energy, which is a factor of velocity squared. So we see quite a lot of improvement in the effective kinetic energy through this diagram. So here we have a little bit of discussion on mass loading. So this is just holding 30 bar and trying two different temperatures. So we've put in the copper particles and we've changed the mass rate at which we're feeding those particles. That's what's on the x-axis down there. Different mass rates, and the two lines each represent a different operating temperature. And you'll see that as we increase the mass loading, so that we inject more and more powder into the nozzle, you'll see that the particle groupings are slowing down in velocity. This is what we expect, but it was great to be able to map out precisely how that works. And of course, it does seem to be asymptotic. So it seems like at some point we can just keep increasing the particle loading if we don't mind the pressure being lower than it might be otherwise. So yeah, I guess the short answer here is for those of you that haven't worked this out yet, if you really want to get the highest possible velocity out of your powder, just inject a very small amount of it into your process and you'll be able to observe the highest cold spray velocity. All right, this is a separate observation to pressure. So in this case, we've operated at our standard pressure again, 30 bar. And what we've done is we've changed our system temperature only, and we've made copper blocks at each of those temperatures. So importantly, you'll see the color of the copper changing quite dramatically. So there are actually publications out there that look at estimating the oxide thickness on a copper depending on its color. That is a thing. And indeed, what we're seeing is an increase in the oxide layer coating the part as a result of the part getting hotter as it was being printed. So importantly, this was spraying with nitrogen and not air. We typically spray with air, but in this case, we sprayed with nitrogen. So we weren't getting hot oxygen off of our nozzle. So all we were doing was heating the part up with the nozzle, and the ambient oxygen around the part, even under that nitrogen shield, was still enough to oxidize the part pretty comprehensively. So I guess this is a note for those of you that might be wondering that indeed spraying with nitrogen and not filling your chamber with nitrogen means your part will still oxidize. So we've got the numbers here. Okay, a bit of analysis in general. So again, this is at 30 bar. So what I'm trying to demonstrate here, this is a thing that a lot of cold spray processes don't offer the opportunity to do, is some basic heat treatments. So in this case, we're not trying to sinter the material. We're just trying to heat it up a bit, improve the interparticle boundaries, relax some of the work hardening in the process. And indeed, when we do this, we do see a big improvement in elongation. So at 30 bar, we would typically see maybe between 0.5 and 5% elongation. So fairly low elongation. But you'll notice in that min elong column, the third column along, the elongations are actually quite high. So, 15 to sort of 28%. So just a very mild heat treatment is enough to recover ductility pretty substantially. You'll see that the yield stress has dropped as well, which is something we expect just with a bit of grain growth. But also, of course, on the right, you'll see our powder deposit efficiency It's very high for copper. Everyone who's cold sprayed copper knows that. The right materials will spray with very high deposit efficiency. So really, one question that's always been in our minds is, as we're cold spraying, we know that we're adding heat to the part. We know that that's causing oxidation. Okay, but if we do see annealing behavior at low temperature, is that of benefit? We're effectively doing some heat treatment with the nozzle as we spray. So Andrew Dugood, our chief metallurgist, presented on this subject last year at CSAT 2024, where he saw significant sintering-like behavior, so improvement in both strength and elongation at as low as 100 degrees C, so 210 F, which if you're a powder metallurgist is suspiciously low. You wouldn't expect to see any of those kind of behaviors. So it's some of these new factors that we're starting to see reported in cold spray, like dynamic recrystallization. The microstructure is recrystallizing in a very beneficial way with a little bit of heat. So we observe that as well. So two ways to get elongation. One is to increase the pressure. The other is to do a heat treatment afterwards, even a light heat treatment in the case of copper. Okay, here's some fairly detailed results on the high pressure cold spray. So I've included these really so people can go away and have a bit of a play. I've tried to include some interesting numbers in the columns. So for example, I've calculated the effective power in the gas flow, that's column 5, and I've calculated the kinetic energy per particle in microjoules, that's column 7. So I haven't been able to do anything significantly useful with these numbers, but nevertheless, they're calculated for interest. So what I've done is I've sorted these results during a variety of temperatures and pressures. I've sorted them by hardness. So that's the orange column there, from low to high. And so, of course, what we see at first is that some of the higher powers in the gas correlate with the lower hardness, and the higher nozzle temperatures also correlate with the lower hardness. And indeed, it's not quite monotonic, but you'll see that the elongation is also correlating with the lower hardness. So these are somewhat similar effects to if we were to take the part out after spraying it at low pressure and then heat treating the part. So we're definitely seeing more than one effect here. We're not just seeing an in situ heat treatment as a result of the additional power in the gas as a result of the higher pressure. But I think the hardness is definitely telling us that we're seeing some annealing in process. There's quite a big range there, 50% in hardness as we go from the hot, high temperature, high pressure gas down to the cooler gas. There's quite a big difference there. And indeed, those hardnesses correlate with the yields, which would suggest an annealing type behavior. But interestingly, the UTS doesn't substantially change. So if anyone's got a theory about why that happens, let me know. We haven't been able to work that one out, but it's a fascinating result all the same. So annealing does explain some of it. So I've got a little cartoon of Hephaestus, the Greek god of metallurgy and material science, looking confused and scratching to his beard and thinking to himself, well, I think there's annealing in here. So I genuinely think there's annealing in there, but there's something else going on because we're seeing good retention of mechanical properties as we improve the elongation. So there's this dynamic recrystallization phenomena that we're seeing in more and more cold spray papers now. And so we haven't done the detailed SEMs, but I think if we did, we would see that phenomena. So we're planning to do that soon. All right, so this is a little chart that we put together. I did put this in my CSAT talk, but I didn't get much time to talk about it. So this is from Andrew, our metallurgist. So the thought is this is something we want to donate to the community. It's a bit of a blueprint or a map that talks about what happens when you increase the nozzle energy. So temperature or pressure, either one. What does that do to the material? So turn it up to 11. As I say, spinal tap. So first three things that you see increased peening stress. The particles are hitting at a higher velocity. They're work hardening more. Therefore, you see increased peening stress. Okay, residual stress, we understand that one. Second one, there's a higher thermal input. So we're putting more heat energy from the gas jet as we cross across the part. So that has effects. Thirdly, of course, we're seeing more adiabatic shear. So as the particles are striking, there's more of this very highly plastically deformed zone being created as we increase the nozzle energy. So we see more of that kind of jetting and cold work type of microstructure. Okay, that's level one. What does the increased pinning stress actually do though? Well, it's generating residual stress, which may balance against the residual thermal stress, depending on where you're operating. And that's important to consider. The thermal input is, of course, giving you partial in situ annealing, which I think we've just proven was happening in that case. But of course, the higher thermal input is also increasing oxidation. So, you know, most metallurgists are kind of live in fear of oxide. I keep joking there's a race of argon-breathing aliens that have better metallurgy than us. Oxygen and metal really doesn't mix well. And as we increase the thermal input, even if we're using an inert gas to spray, we do see significantly increased oxidation as a result of the higher part temperature and the higher gas temperature heating the part up. Lastly, the higher jetting and cold work does lead to reduced fracture toughness. So this is something we've seen. Those of you that have done fractography and cold spray will look at the broken ends and you'll see that the particles, you tend to break at interparticle boundaries, and indeed where you're getting those jetting zones, which provide a lot of hardness and not a lot of toughness. So what does that mean? If you're not careful, you get green cracking as you're spraying the part up. The residual stresses will overcome the strength of the part and you'll start to develop cracks. Very material dependent, very thermal conductivity dependent. You see fracture toughness variability, which affects some people, but most importantly, down the bottom there, we get these interlayer pores as a result of the oxidation, which do need to be managed. So depending on what you're doing, that can be an important factor as well. And what that will mean is you'll have great strength if you've been spraying this way. You'll have great strength laterally, but as you come in between the layers, you'll start to see reductions in strength. So in cold spray AM, as opposed to just cold spray, we have to think much more seriously about those planes of oxide and managing those, because we get poorer properties typically in Z. So that's to the extent where when we're developing a new material, we won't even look at XY properties until very late in the piece. We will just look at Z. It's a dominating factor. All right, that's the end of my presentation. So I think we're pretty much on time. Yes, so thanks very much for your attendance and happy to take some questions.
Awesome. Thank you so much, Steve. That was a wonderful presentation. Reminder to the audience, please use the Q&A tool if you have questions that you would like to submit. I certainly have a number of questions. So I'm going to start out while we wait for a few to roll in. So Steve, really early on in the talk, you had specifically mentioned that you guys have optimized the nozzle to be stable over a really long time, which is critical for AM. Can you talk a little bit about why that's critical for AM, and then also what that means physically with what you all have done for your nozzle configuration to ensure that you do have that stability over a long time?
Yeah, okay, so this is a very good question. So I guess this is why it's important to be a freight truck and not a Lamborghini. So you know, if you're making a Lamborghini, nobody really expects a Lamborghini to be an awesome courier vehicle. You know, it's not very good at carrying packages, and it needs a lot of servicing, and presumably the tires are expensive. So, but if what you want is a Lamborghini, if you're doing material science and you want your cold spray nozzle to give you the absolute highest velocity, then you'll construct the nozzle in such a way so that depending on the powder, you know, you can kind of meccano build up your nozzle and optimize every part of it to give you the best possible velocity. So that's very important for that market, but that's not really the market that we're in. So we might, for example, print 200 pounds of material in the case of a Titan printer in one part. So when you're typically building a part that large, you've got to treat the process more like a manufacturing process. So manufacturing processes require good predictability. So what that means is every portion of the material, every kind of unit of volume in that part needs to have been made with a process that did as you expected. So you can't have, for example, throats on your nozzle wearing dramatically and changing the gas consumption, because that'll change the deposition performance. You can't have clogging and buildup in the nozzle, even if it's very gradual. If you're printing for a whole day, for a whole 24-hour period, that'll mess you up, because the material properties will be changing as you go. So we've really had to work very hard to make sure the nozzle itself gets minimally kind of affected by the cold spray process. So you want it to be as reliable as possible. You want to minimize erosion. You want to minimize clogging, and doing that cheaply and ending up with a nozzle that's kind of commercially available and reliable is a very difficult engineering task. So we've put a lot of time into that, which I'd guess, and we probably have other cold spray vendors here. I guess most people don't think about that very much, but that's been a dominating effect for us. Yeah, did that answer the question?
Sure did, thank you.
Yeah.
I have a couple audience questions for you. One going to the interlayer bonding discussion and what those interlayers and defects look like. Do you have any images of that? And I guess probably a good follow-on to that is, what is the nature of that defect, and do you think there's a way to improve upon it too?
Another good question. Okay, so look, I'd be very happy to have a follow-up discussion with this person. If they want to contact me, with a very welcome. But yes, there's a lot of good information on this. I think Swinburne, so Nirvana and Suresh from Swinburne in Australia, in Victoria, did a paper on this in maybe 2020 or 2021 in the case of copper. So air sprayed copper. So what that means is, you spray a layer of material, and then as you're spraying that layer, the oxygen's getting into that hot material and it's forming an oxide layer on the surface. And then the nozzle comes back and adds another layer. And you end up with this trapped layer of oxide in between the two layers of copper. And you do see some more porosity, in that plane as a result of that. It's not significant, but it's definitely observable. And the oxide itself, of course, is much more difficult to observe. But if you then do an as sprayed Z tensile specimen, it will almost certainly break on an oxide boundary, and you'll be able to see the oxide either side of the tensile specimen's fracture surface. So we call that latency oxide, because it's an oxide that's happening as you're between layers. So as I mentioned, spraying with nitrogen isn't enough to prevent that from happening. You've really got to inert the chamber to prevent that from happening, which is a larger exercise and not something our machines do easily out of the box. But if you're very, very oxide sensitive, you need to look at those kinds of remedies. So yeah, did that cover that, Brad?
Yes, I think certainly. And whoever had asked that question, as Steve indicated, if you want to touch base with him on that stuff, he has loads of information on that. Next one from the audience. Steve, you mentioned a high pressure system. And of course, the question comes in, when can we buy it?
Yeah, it's a good question. So we're currently looking at that. So the intention is to work on a refit of system of some sort, so that our people that already have a system can elect that option if they want. And we'll probably make it. It'll probably make it into production machinery very, very soon. But we're still gauging the interest in that. So amongst CSAT, I guess we've got a bit of survivorship bias here. We're probably talking to the people who are most interested in having that feature. But the machine's still incredibly useful without high pressure. Most people will be heat treating their material, and it doesn't hugely impact on the properties if you're heat treating. So whether or not people want to pay the additional price that's going to be involved in those additional systems, we're still kind of researching. So I would say we're probably going to see, at a guess, that refit being available in sort of the next 6-9 months, something like that. So that's something that we're actively working on right now.
Wonderful. Had a question on your Hephaestus slide and the, I guess, lack of a relationship between the hardness and the ultimate tensile strength.
This
Which
one?
I agree. Yep, and I agree with the audience member here asking this. It's really, really interesting and curious. Question specifically from the audience was, what is the configuration for the test of the ultimate tensile strength? And I guess to that extent, and what orientation are you testing to is also a good question.
So, sorry, what's the
Is it,
configuration for the tensile test?
yeah, is it just a conventional dog bone, and is it an XY dog
Yeah.
bone or a Z direction dog bone?
So I think it's an XY ASTM E8. I think micro specimen. It's about 100 and 120 millimeters long from memory. Planar specimen with about a 6 by 3 millimeter test section, something like that. So pretty standard. It's ASTM compliant, and we do that. These results came from an outside lab that we use.
Yeah,
Yeah, sorry,
just
what
looking
was
at
the
it,
second part of the question?
I think you got it there. Looking at it real quick, my quick thought on it, by the way, is your UTS is consistent and your yield and hardness are going in about the same direction. I wonder if you're
Yes.
effectively getting different cold work levels of the copper, right? So you're going from quarter hard all the way to full hard, essentially, on your copper there, because that doesn't change the UTS, but it does change the yield strength and the hardness.
Yeah, so I mean the yield strength and the hardness do correlate extremely tightly, which I guess is relatively expected. But yeah, it's a good point. If there's more work hardening in the material, I guess we would expect to see a higher yield and less elongation, leading to roughly the same UTS. I guess I just didn't expect the UTS to change so little through this whole random test matrix.
It is
It's
shockingly
almost,
stable.
yeah. And I mean, tensile testing, as I'm sure most people know, is not the most reliable, like gauge R&R reproducible process in the world. So to see it with that small a band on it was really quite impressive.
Yep. Okay, I have two more for you myself.
Okay.
So I think hit those two, and then maybe we'll let everybody loose. So you had mentioned pretty early on building. We're effectively building a powder metallurgy compact, right? And I know you and I have talked
Yep.
about it, but I think this is a really interesting idea. And so I would just like to hear you elaborate a little bit more on what your thought process is there. What are the similarities and differences between what you guys are doing and the traditional PM approaches? And I guess overall, why do we want to think of it as PM versus how we're more traditionally thinking of other AM processes?
Yeah. So this is a deeply philosophical question, which I really like. We've been thinking about this a lot. So okay, powder metallurgy is a process of taking a powder and then turning it into a compacted specimen of some sort, and then usually sintering it to form a material and a shape. So indeed, the process that we've described here, so this process here, where we compact the powder using a cold spray nozzle and a robot, and then we take that compact off and we heat treat it. Indeed, not in this paper, but we do sintering, including very advanced forms of sintering, which we've taken really from the great body of literature in PM. It's incredibly effective on cold spray compacts. So, for example, our nickel, aluminium, bronze, I think I presented on that at CSAT last year. Anyone who's interested in that, we used a blended elemental metal approach to form a compact, and then we used liquid phase sintering to form the alloy. So it's an alloy that's made of copper, aluminum, nickel, and iron. And we literally took the powders, we blended them together as though we were making a cake, and then we sprayed them together, and then we heat treated them in a process called liquid phase sintering, which let the alloy form and quite homogeneously without changing the shape of the part. So that's an incredibly useful process. So we can take compacts straight out of this process, and we can throw them into a HIP, and we can get something that's very like a HIP PM part but we don't need the can, and we don't need to evacuate the can. So that's quite advantageous as well. I mean, all of these processes are powder metallurgical in nature. You're taking a powder and you're using the deep level of control that you have because you can physically manipulate a powder, versus if you're melting it where uncontrolled processes happen. And as a result of that, you can form a shape, and you can form a material composition. It might be a graded composition or a exotic alloy, which you can then form by heat treatment with standard PM routes. Now, the key difference, first of all, there's all the cold spray goodness that happens. So the high density, very high, usually over 99%, versus PM, typically 80 to 90%. So we don't have to worry about as much gas, as much void being in the part as PM people do. We have an advantage. If as a PM process, it's advantageous over pressing. And indeed, we also get this additional cold work and dynamic recrystallization, for those that believe in that, which gives us beneficial material properties as well, which you don't get at all in PM. It's very unusual to get any kind of dynamic behaviors in your compact in PM. So if you think about cold spray as a particle by particle pressing process, then indeed what we're doing is a standard PM route for making a material. We press and sinter. So it's an unusual lens to look through when thinking about additive manufacturing, but we're finding more and more it's a benefit to think about it that way. So yes, we've decided to come up with a name of that process, which we call EPIC, so extreme particle impact consolidation, as a method for forming material by cold spraying a bulk and then sintering the bulk. Yeah, sorry, Brad, long answer. Did that cover you?
Yes, absolutely. It was a great answer and exactly what I was looking for. Okay, very last one from me, and then I think we'll probably cut out a handful of minutes early here.
Yep.
You had mentioned twin speed and the origin of the name twin speed being a digital twin of the part, which is actually really cool, and I haven't thought a lot about this before, but I think there's something really neat and interesting to be said in that you guys actually are building the digital twin from a very sophisticated simulation before you even build the part. Have you talked about or looked at comparisons between your digital twin, both during the print, after the print, and after heat treatment and finishing? And also, have you looked at defect prediction and defect detection in the context of having this super high fidelity digital twin?
Yeah, so very good question. So we've done a lot of different kinds of study. So fundamentally, the reason why we developed the software in that way was because we really wanted to know, firstly, what the toolpath would do to the geometry, which, those of you that have ever done handheld cold spray will know it's not really super predictable what'll happen. So we needed the simulation kind of for our own sanity when we were developing, the first processes to toolpath automatically. But, it also gives you a very direct feedback. So if you've done something that turns out not to be manufacturable and it results in an odd shape, you'll see that, like the simulation will show you the good and the bad, honestly. So that's what a good simulation should do, I think. So we have done quite a lot of testing comparing the way it can work and not work in terms of generating geometry to what the printer does. And we did a huge amount of that, roughly 10 years ago. And, it's quite accurate. There are a few edge cases where it's not, but in general, it's quite accurate. But of course, the thing that we're really interested in seeing is what are the material effects generated by the toolpath. So if we can toolpath it in 3 different ways, that would probably generate 3 subtly different kinds of material. So this is our next field of research: is how do we optimize the material? How do we give it preferred properties by toolpathing it in a particular way, choosing to toolpath it in a particular way. So this is kind of where we're up to with that work.
Fantastic. That closes it out on my end. I am not currently seeing any other questions from the audience. Again, Steve is, of course, willing to directly answer your questions if you'd like to follow up with him. So that closes out the 2025 CSAT webinar series. Of course, there will be more webinars throughout the year, and we'll do this whole thing again come 2026. Steve, thank you very much for a wonderful presentation, and to all the audience, thank you for attending. And we'll see you soon.
Thanks for hosting, guys.
Have a good one.
Bye.